Swayam Prabha. Digital India. Educated India.
Good day everyone. This is the 13th lecture, and in this lecture we will talk about Euler angles and orientation distribution functions, which is abbreviated as ODFs. The concepts that will be covered in this lecture are Euler angles and Euler space in detail, what is orientation distribution function or ODF, and we will give you an example showing the rolling texture of face centered cubic material and relate the pole figures and the ODF and the Miller indices. You see, what is an Euler angles? And I have been telling this in the past lectures that the orientation location space can be related by 6 variables, that is phi 1, phi 2, and that phi 1, phi 2 is the angular variables, and x 1, x 2 and x 3 are the positional variables. So, you see Euler angles are actually that phi 1, phi 2, that is the 3 variables that are required to specify an orientation. Now, why Euler angle is used? Because you see Euler angle representation gives you the information of the texture in 3 variables phi 1, phi 2 instead of 9 variables of the orientation matrices, and therefore, it is very convenient to a way to describe the texture. Now, you see why it became very convenient, because while a texture is measured, there are multiple points from where the texture is obtained in a microstructure. Say for example, in the case of electron backscatter diffraction, and a software is used to obtain the overall texture information. When texture was developed in the earlier times in 1965 and later during 1970, 1975 and 80s, then the computer programming or the computer hardware were not so equipped enough to handle big data, and therefore, the Euler angle representation using 3 angles phi 1, phi 2 became more convenient way to describe the texture, because instead of solving 9 different variables, only 3 variables were need to solve per pixel points in obtain the overall information of the texture using the software in a computer. So, you see what is Euler angle? What are Euler angles? Euler angles are 3 rotations which, when performed in the correct sequence, transforms the specimen coordinate system into the crystal coordinate system, right. So, the coordinate system is basically known as the Euler space. So, if you see phi 1, phi 2, it is 3 angles. So, this angles can be used to form an angular coordinate system, and can be a space can develop, and this space is known as Euler space. So, there are 3 ways of doing this. One suggested by Bunge in 1965, another was suggested by Roy, and another by Williams. So, you see one can obtain this phi 1, phi 2 rotations differently, right, in order to make the sample coordinate system equivalent to the crystal coordinate system. That is the path by which the sample coordinate system travel angularly to get to the crystal coordinate system, and that path is basically the texture, and it can be done differently. One way was suggested by Bunge, another way was suggested by Roy, and another by William independently and separately. But you see, with time most of the scientists started following the Bunge's notation of measuring the Euler angle, but it does not mean that the Rowe's or the Williams way of measuring the Euler angles were not correct. All were correct, but the popularity was gained by the Bunge's way of measuring the Euler angles. So, you see Euler angle or Euler space phi 1 phi phi 2 is the relationship between the sample coordinate system and the crystal coordinate system. Say for example, we have a rolled sample with important sample reference directions. As I said, we will take the rolled sample or the rolled material only as a reference material, because most of the students are more familiar with the rolling and the rolled material and the important sample reference directions of the rolled material, which are R d, the rolling plane which is perpendicular to N d, and the rolling direction which is R d and T d, right. So, if you see that if we take a sample like this and we have many grains in it or many crystals in it, and few crystals have this orientation, few crystals have these, and but even though they have, say for example, this orientation, the grains would be spatially separate out, right. Now, you see that if this particular orientation is present in a large amount, then the intensity of the texture from this orientation will come highest. So, we will consider that this is the most intensified texture in the material. Now, you see that if this is R d, this is T d and this is N d, and if this crystal has the coordinate system 1 0 0 0 1 0 0 0 1 like this, then how to find out the rotation sequence proposed by Bunge, that is the rotation sequence phi 1 phi phi 2, in order to take this crystal coordinate into the take this sample coordinate system into the crystal coordinate system. So, let us see this schematic which is made of from this, and it is little different, but you see the R d, T d and N d is similar, and the 1 0 0 0 1 0 and the 0 0 1 of the crystal is also in the similar position at this as this figure. Now, you see that the Bunge's notation states that there are 3 rotations. So, the rotation 1 is phi 1 and the sample is rotated along N d, that is the normal direction, right. And then after some time a rotation 2 which is phi, where the sample is rotated along R d, right, and then the sample is again rotated along N d, and this is known as the third rotation phi 2. And let us see what was the Bunge's sequence. You see that if we look into the rolling plane of the sample, the rolling plane will contain R d and the T d, and the N d will be perpendicular to this rolling plane. So, here we have drawn the plane which contains the R d and T d in this red and pink color, right. And let us draw the plane which contains the 1 0 0 and the 0 1 0 crystal system, that is the plane 0 0 1 plane, where the 0 0 1 is basically perpendicular to this plane, and this is that plane which contains the 1 0 0 and 0 1 0. So, you see if we rotate N d, and we will use the right hand thumb rule to rotate the N d, what happens that the R d will start to move in this direction and the T d will also start to move in this direction. So, how much we will move R d? You see that the R d will move up to such a point where the two planes basically meet. Now, what is that plane? You see that this is one plane which is the rolling plane, and it contains the R d and the T d. On the other hand, this is another plane, as I said, which contains the 1 0 0 and the 0 1 0, that is the 0 0 1 plane. Now, there is one line where both of this plane meets, and this line passes from the origin and it goes somewhere like this, right. Now, if this rotation phi 1 is given, then the phi 1 is given in such a way that the R d basically rotates by phi 1 to go and meet that intersection line between these two planes, right, and the T d will automatically move or rotate, maintaining the angular relationship between the R d and the T d. So, this is the first rotation where we need the R d to be in the plane in this plane and also in this plane, right. So, now you see that once R d is rotated, the second rotation phi is along this new R d, right. And when we rotate this new R d by phi, the rotation has to be such that the N d will now move to 001. And how it is possible? Because you see the R d now lies in this plane, that is the 001 plane 2. So, once the phi is rotated by the right hand thumb rule, what will happen? The N d will move and go to 001, and that is the phi rotation, where the T d will also move up and meet this plane, right. So, here is the rotation, and you see the new T d and the new N d, right, whereas the R d remained constant because the rotation took place along the R d. Now, we give the phi 2 rotation, which is again using the right hand thumb rule, and it is given on the N d. So, as because this is the new N d, the rotation is given, and this is the right hand thumb rule, and you see that what happens, that the now the T d the R d and the T d is now rotated, so that it meets the 100 and the 010, and so that the sample coordinate system and the crystal coordinate system becomes the same. So, this path of travelling, angular path of travelling for the sample coordinate system with respect to the crystal coordinate system, that is phi 1, phi 2, basically gives the information of the orientation of the material, and this rotation is basically known as the Euler angle, and the space that is made by this rotation, that is phi 1, phi 2 space, is known as the Euler space. So, the Euler angles can be used to produce an Euler space, that is, you see I have shown a schematic of an Euler space with phi 1, phi and phi 2 like this. So, it is a space like this, with you see as it is a cubic crystal, and we are working on the cubic crystal for demonstration this time. So, you see what we have done is that using the symmetry of the cubic crystal, that is 100 has a 4-fold symmetry. So, after each 90-degree rotation, it should show the same crystal as before the rotation. So, you see we have taken a Euler space from 0 degree to 90 degree and 0 degree to for the phi 1 and 0 degree to 90 degree for phi and 0 degree to 90 degree for the phi 2. But you see that before we will have to discuss this symmetry relationship in terms of crystal symmetry and sample symmetry, and that we will do in the later course of this course. But just to let you know that the symmetry of the cubic unit cell leads to reduce the size of the Euler space from 0 to 360 degree for phi 1, phi and phi 2 to 0 to 90 degree at this time. And you see the Euler space which can be seen like this, displays the distribution of the complete orientation in a 3-dimensional orientation space, right. Say we have shown this with an example for an face centered cubic material which is rolled. You see that a face centered cubic material which is rolled, or in general terms show, you see rolled and recrystallized texture, shows a copper texture a brass texture, a gauze texture and cube texture. There are other texture also, like the S component is shown, but for this example I have shown you only this 4 texture. So, you see that the position of the cube texture is shown by the blue. So, you see it forms here, that is at phi 1 phi phi 2, that is 0 degree, 0 degree and 0 degree, and it forms here, that is at phi 1 equal to 0 degree, phi equal to 90 degree and phi 2 equal to 0 degree. Like that it forms here, 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 and it, you see it forms like a fiber in this position, and we will look into this in the later lecture, that why this kind of fiber is being developed. Now, you see if we look at the gauze texture, which is given by this orangish color, and you see it forms here, it forms here and it forms here. So, you see that the same texture forms at various position, right, because of the symmetry of the crystal. So, you see the cube which is 0 0 1 1 1 1 0 0 forms at the 8 positions or 8 corners, and it also forms at the fiber diagonally at phi equal to 0 section, right, phi equal to 0 section. Now, you see gauze which is 0 1 1 1 0 0 forms at 3 different positions. You see brass which is shown in the bottle green color also forms at 3 different positions. On the other hand, you see copper also forms here and here. But you see, while demonstrating this texture components using our Euler space, visualizing this and the position, the angular position of each of this cube, gauze, brass and copper component becomes extremely difficult, right. So, what we do is that we take this Euler space and we represent this 3D Euler space into a 2D representation, and this 2D representation is known as ODF or orientation distribution function. So, what we do is we take this Euler space and most of the time we slice it like a like a bread along phi 2. So, we slice it, for example, we show this phi 2 equal to 0 section, and then we go below and show the phi 2 equal to 5 degree section, and then 10 degree section, and then 15, like that we go and show the up to the 90 degree section, which is which gives you a 2D representation of this 3D Euler space in form of an orientation distribution function. So, you see this orientation distribution function basically describes the volume fraction of the crystallites having the orientation of the crystal axis with reference to the fixed coordinate system R d, N d and T d, then that is what the definition of the texture is, right. So, you see if we take the first section at phi 2 equal to 0, we obtain, you see, this kind of a ODF section which has phi 2 equal to 0, and it goes from 0 to 90 degree phi 1 and 0 to 90 degree along phi, right. And then we can take another section which is just below this section, and then we can say that okay, this is a 5 degree section. So, we are taking 5 degree, and then we are taking at 10 degrees and 15 degrees and 20 degrees, and like that we take all the sections up to 90 degrees, and thereby we obtain this same information in 2D. But now, you see that it is easier to perceive this information than to perceive the information that is present in 3D. So, in ODF we observe the the volume fraction of a particular orientation G with respect to the volume fraction of the whole orientation, right. So, you see that it gives the intensity in terms of volume fraction of a particular orientation present. Now, let us see how the cube, gauze, brass and the copper texture in this ODF looks like, and how we can compare this with this 3 dimensional Euler space. You see the cube texture forms basically here, right. And so, it is at phi 1 equal to 0, phi equal to 0 and phi 2 equal to 0, right. On the other hand, you see at phi 2 equal to 0 section, the cube texture forms here, here, here and here. So, you see we obtain the cube texture here, right. On the other hand, as because of the symmetry at 90 degrees, similarly the cube texture may develop at the 4 corners, which develops and can be observed from this 3D Euler space. We can see that this cube texture you see can form, and I have shown by the blue colored square boxes. Now, you see that like that we can observe that as the phi 2 sections are increasing from phi 2 equal to 5, 10, 15 to 90 degree, this fiber which forms because of the cube orientation always shows itself as component at with increasing phi 2 at various positions. You see at phi 1 equal to 85 degree and 80 degrees, and you see 75 degrees like that, and it goes here and it becomes 45 degrees here, and it goes here and it becomes 85 degree and then becomes 90 degrees. So, that fiber could be observed throughout the whole ODF phi 2 equal to phi 2 sections, right. Now, on the other hand, you see gauze texture can be observed at phi 2 equal to 0 and phi 2 equal to 90 degree section, and then you see brass texture can be observed at phi 2 equal to 0 and 90 degree sections, and it is also present here, which I have not shown, right. Hey, these brass texture, right. Now, you see we can observe the the copper components, and which is present here, and so you see that one can distinguish more easily the various texture components or fibers that are present in the material using the ODF rather than using the Euler space, right. So, because visualizing a 2D picture is much easier for us to perceive than the 3D. So, we use the 2D ODFs to observe the texture, not the Euler space most of the time. So, you see when we talk about texture, and we mostly are concentrating on cubic materials, and we are concentrating on rolled material, because there are lots of research on it and lots of publications on it, and we can relate, there is a whole bunch of literature of texture relating the rolled material. So, you see we give an example of rolling texture of face centered cubic material, and here are the 111 pole figures, and we see that the texture that forms for the pure material, that is the copper type texture, is something like that, and for the brass type texture it looks something like that. So, there is a subtle difference, and then we see the copper components and the S component and the brass components were distinguished in them, and you see that the difference between the orientation, the difference between the texture developed for the copper type and the brass type texture is because of the effect of stacking fault energy, and we have discussed a little about this before. But as you know that high stacking fault energy material during the deformation has the facility of cross slipping of screw dislocation and the climb of edge dislocation, leading to easy dynamic recovery, and thereby form this kind of texture. Whereas, in case of low stacking fault energy material like single phase alpha brass, they deform, and where the distance between the partials 112 partials are so large that it cannot the screw dislocation cannot cross slip to another plane, because the partial cannot come together to form a full dislocation, and therefore, it cannot cross slip, and therefore, the climb of the edge dislocation is also restricted, and that leads to restriction in the dynamic recovery processes, and thereby the deformation is restricted, and then deformation twinings also develop, and so the texture basically changes as the stacking fault energy of the material changes, and this is known as texture transition. And so, you see that the copper type, S type and brass type texture that are shown in the pole figure could be related to the Miller indices, and we have seen that each texture component present in the pole figure or the inverse pole figure could be related to the Miller indices, and then these texture components can also be shown in the Euler angles because they are related. So, the position of the copper texture in terms of Euler angles, say it is 90 degree, 30 degree and 45 degrees, phi 1, phi phi 2. For the S it is 59, 34 and 65 degrees for the phi 1, phi phi 2. Brass forms at 35, 45 and 0 and 90 degrees at phi 2s. Gauss forms at 0, 45 and 0 and 90 degrees at phi 1, phi phi 2, right. So, these are the information of the experimental texture that develops in the face sintered cubic material during rolling process. Now, these texture could be represented using the Euler space, and this texture is more easily represented using the orientation distribution function. And here we are in the next slide I am showing the texture, the ODFs, that is phi 2 equal to 0 to 90 degree section for both the high stacking fault energy material, that is copper type texture, and low stacking fault energy material, that is the brass type texture, in terms of phi 2 equal to 0 to 90 degree ODF sections. And here it is. You see that the components, that is this is for the high stacking fault energy material, that is pure copper texture. One can observe the formation of the gauss, the formation of the brass texture. The gauss is weaker as compared to the brass. Now, you see the the copper component has formed. The copper component is the strongest here, and this has been shown. So, the copper is the most strongest, and then the S component is present. The S component is also present stronger here. So, the copper and the S component is stronger and the brass is weaker and the gauss is more weaker, right. On the other hand, you see that in case of the low stacking fault energy material, what has happened, that there is a substantial amount of brass component present in it. So, the brass component is very stronger and the gauss is a very weak, and then you see that the copper texture has not even formed properly, and you see the S component is there, but it is weaker as compared to the high stacking fault energy materials texture. So, you see that the 90 degree section, the 90 degree phi 2 section and the 0 degree phi 2 section shows exactly identical type of texture, and you see because of the symmetry of the cubic crystal. So, we can observe the the subtle difference between the texture developed after rolling of a high stacking fault energy face centered cubic material and a low stacking fault energy face centered cubic material using the ODF sections, and this could be related to the pole figure and the Miller indices, because they are mathematically interrelated and they are different tools to represent the texture. And you can see that most of the time we use phi 2 sections and we divide the sections at 5 degree graduations, sometimes at 10 degree graduations, or sometimes we show the most important phi 2 sections. It does not mean that we cannot show the texture using Euler angles in other sections. There are relations which can be observed when we observe the texture in phi sections or phi 1 sections too. So, that is all for this lecture, and we can conclude that 3 rotations phi 1, phi 2, if done in correct sequence, can transform the sample coordinate into the crystal coordinate, which is required to specify the orientation, and this is known as Euler angles, right. Bunge, Roy and Williams all did this using different rotations, but all of them are right, but the Euler's angle proposed by Bunge has become the most popular. Euler angles can be used to represent texture in 3 dimensional orientation space and is known as Euler space, right. The 2D representation of the 3D Euler space is known as orientation distribution function, that is the ODF. The ODF describes the volume fraction of the crystallites having orientation of the crystal axis with reference to the fixed sample coordinate system, right. Different texture components, for example, cube, gauze, brass, copper, S components, this is an example for FCC, rolled FCC material, can be distinctly observed at various phi 1, phi 2 positions of these ODF sections. The Euler angles phi 1, phi 2 are related to the important sample reference planes and the direction, and could be indicated by the Miller indices HKL UVW. Thank you.